Hello and welcome to today's coding challenge, Wave Function Collapse. This was originally suggested in 2017 on the Coding Train's GitHub suggestion box. The algorithm itself was originally pioneered by MXGMN on GitHub in this wonderful repository with lots of sample imagery and explanation. The core idea of the wave function collapse algorithm is to take an input image and generate an output image, many output images that all mimic the style, the pattern of that original image. Now you might be thinking, aha, don't we have giant deep neural networks that can do this? Yes. But this algorithm is incredible because it uses none of that, and it is just a joy to watch. I should say, if you're here thinking, oh goody, here comes a step-by-step tutorial on how to implement the wave function collapse algorithm, it's probably not what you're gonna get. I have not done it before, other than a brief failed attempt that didn't get very far, so I'm here to try it again. What you're seeing to the left and right of me is hopefully the end result of this video, and if I've gotten there, if I've succeeded, it hopefully looks interesting and like something you might want to watch. So stick with me, all aboard, let's try to make wave function collapse happen. In addition to the GitHub repository, which has the source code for the original implementation of the algorithm, as well as a full explanation of the algorithm, as well as many links to forks and spin-offs and variations of it, the other resource that I am following closely for this challenge is the wave function collapse post on the processing forum itself. Thank you very much to Salab, who started this thread. Tons of great information there. I highly recommend you take a look at all the explanations and diagrams and source code as well. Let's begin by answering the question, why is it called wave function collapse? While this is an algorithm for procedural generative images, which could be applied to art and games and so many different kinds of creative things that you might try, the term itself comes from quantum mechanics. What does it mean to collapse a wave function? To answer this question, let's talk about another term, entropy. I want to talk about entropy in the context of information theory. If you're a fan of the game Wordle, there's a wonderful 3 Blue 1 Brown video that goes through how to optimize your solution for any given Wordle of the day with the concepts of entropy and information theory. I'm going to attempt to explain it to you in the context of a different game, Sudoku. Sudoku is a game where you fill an entire board with the digits 1 through 9. Each digit needs to appear uniquely in every row, in every column, as well as every 3x3 section. This means if I have a blank Sudoku board, every cell has 9 possible digits that could be in it. The average entropy of this system we could think of as 9. What's exciting about the concept of entropy as applied to games like Wordle or Sudoku is when we know some additional information, like, aha, we see the board comes with one number already filled in, like the number 9 here, then suddenly the entropy is reduced for these 2 cells, all of these cells, all of these cells, and all of these cells here, right? All of those cells only have 8 possible numbers that could go in them. If I were to say that there's a 2 here, then suddenly all of these cells only have 7 possibilities in them. And how does this relate back to wave function collapse and quantum mechanics? The idea of collapse in the context of entropy is to collapse all the possible states down into one, remove all the entropy from a single variable of the system. So this cell in Sudoku is collapsed to 9. This cell is collapsed to 2. As certain cells collapse and their state is revealed to be a single option, the entropy is reduced for its neighbors, and we can start to make guesses there and further collapse and further collapse and further collapse until we've solved the Sudoku board. I'm going to start over with an example Sudoku board that I got off the internet. The process of solving a Sudoku puzzle is exactly the same process that lives inside the wave function collapse algorithm. The idea is to start with a set of tiles. In this case, many of them have been collapsed already, and look for the tile with the least entropy, meaning the fewest possible numbers that could go in it. So I'm going to look at this for a minute here. Let me use my brain power. So I've been going through and noting what numbers are possible in any given tile. And as I was working through it, I noticed, well, there has to be an 8 down here somewhere. And there can't be an 8 in either of these two columns because of these two 8s. There can't be an 8 here, and there can't be an 8 here. So the only possible number in this particular cell is an 8. So I can collapse it and fill in the 8. I'm looking for the tiles with the least amount of entropy, collapsing those tiles, and then going and looking for the next tile with the least entropy, and so on and so forth. If at some point I don't have a tile that has only one option left, I might just have to make a guess and go with it unless I realize I'm stuck and have to backtrack and try a different option. Now that I've finally solved this Sudoku puzzle, we can look at a P5 canvas and try to understand how does the process for solving a Sudoku puzzle map to the process for generating an image through wave function collapse. Now, there are two ways to approach wave function collapse. There's the tile model and the overlapping model. I'm going to start with the tile model. The idea of the tile model is that you have pre-made tiles. I'm going to first implement a tile model with a simple set of 5 tiles. One will be blank. One will have a small line pointing up and a horizontal line across. One with a smaller line to the right, vertical line, smaller line down, smaller line to the left. My P5 canvas I can think of as a 4x4 grid that can have any one of these tiles in any spot on the grid. So right now, the average entropy is uniform across all the tiles. There are 5 possible tiles that could go in any of them. Maybe I pick this tile, then I need to pick one of these random 5 options. Let's say I pick 1 and I fill it in. Now this is all an arbitrary made-up system that I'm doing right now. I'm trying to keep it somewhat simple. The possible tiles for most of these cells is still just 5. However, by placing this tile here, I have reduced the entropy for the neighboring tiles. The only possible tiles that can go to the right are ones that connect to this line right here. That would be tile 4, tile 3, and tile 1. So there are only 3 possibilities here. The only possible tiles that can go here are tiles 3, 2, and 4. I need something to connect to this. So 3 possible tiles. And we're going to see this in all of these. So now if I'm looking for the next tile to do, I want to pick one that has the least entropy. So now I'm only rolling a 4-sided die to pick one of these 4 tiles. Let's say I pick this one, and I roll the dice, and I happen to pick tile 4. Now, the entropy for this spot is now also only 3. Let's say I roll the dice, and I happen to pick this tile. Let's look at what is the entropy for this particular tile now. I need a tile that has connections on both the bottom and the right. Look at that. Only this one now. So only this tile can go there. By the way, I made a terrible error. I was just starting to fill all these out, and I was right about there being 3 possibilities, 3 possibilities, 3 possibilities. This one here actually only has 2 possibilities, because if there is no connector pointing down, then the only 2 options that have nothing connecting to the top are 3 and 0, something with a blank top. So this actually had an entropy of 2. So if I wanted to keep going, I could flip a coin. Maybe I come up with 3. Tile 3, and this goes here. Let's see what happens if I keep going. And voila, I generated this image with wave function collapse. I could run this again, roll the different dice again, and get another image, and another, and another, and another. It took me quite a long time to work this out with my brain and draw it. Hopefully, if we can write the code to load these tiles, to know which tiles go next to which tiles, we can generate these images lickety-split. I am finally ready to start writing the code. All I need is a blank P5 sketch, and then I have here pre-made tiles. blank, down, left, right, up. To start, I'll load all the images using preload into an array. Let's just draw them to make sure they're there. Whoops. I forgot the tiles are in a directory that I called tiles. This algorithm, even though it feels like my explanation is going round and round in circles, is quite simple. I think the complexity here is figuring out what kinds of data structures do I need to hold on to the information about the grid of tiles, as well as which tiles are allowed to neighbor which other tiles. Let's use an array to store the state of every cell in that grid. I want to start with just a 4x4 grid. Actually, let's be even simpler. Let's start with just a 2x2 grid, and I'll use this variable dim, short for dimensions. I'll start with putting a -1 to indicate nothing's been picked yet in every spot on the grid. Actually, no, let's not do that. Let's make an object for every spot on the grid, and I'm going to create a variable called collapsed, which is false. It's not collapsed. And then I'll call it options, and they each should start with all 5 options. This might be silly, but let's set up some variables to keep track of what these index values are. Now I can go through every element and draw it if it's been collapsed. All right, I didn't mean to do that, but I just wrote out a ton of code. Let me walk you through it step by step. So first of all, I need to calculate the width and height of every cell on the grid. That's the total width of the canvas divided by how many columns and how many rows, that dimension variable. Then I'm going to count through every row and every column, find the index into that one-dimensional grid array. This is the same thing I do in all of my videos about the pixel array. And then if it's been collapsed, there's only one option left. So find the correct image and draw it. Otherwise, just draw a black rectangle. So if I'm doing my job correctly, if I were to refresh the page, I should see all black rectangles. And let's actually give them a white stroke so we kind of see this grid. Great. No cells have been collapsed. Let's collapse one of the cells manually just by hard coding it and see if we get the proper result. It's collapsed, and we should see the up tile in it. Options is not defined. Oh, cell.options. And we need to make sure we draw the image the right size. There we go. So what's next? Here I manually collapsed a cell. But what I should have done is looked at all the cells, evaluated and measured their entropy, and picked one that had the least entropy. So let's do that. I'm thinking about how to do this. Oh, let me sort the array. I mean, I can't sort the array. It'll be out of order, but I could sort a copy of the array because I have objects in it. Oh, this was a good thing that I put objects in there because the arrays just point to the object. So I get multiple arrays with the same object, the same data in them, but in different orders. Oh, this is great. And in JavaScript, the slice function will just make a copy of the array. Then I can call the sort function. If I were just sorting an array of words, it would be easy to do alphabetical order or ascending or descending order. But here I've got to define my own compare function in order to say how I'm going to sort them. If this strange arrow syntax is unfamiliar to you, might I refer you to some video I made 100 years ago about the arrow function? But essentially this function is defining, given two elements in an array, A or B, how do I define which one goes before or after the other? And the number of options left for that particular cell is what defines which one should go first or second. Let me just hard code that element 2 only has 2 options. So when I sort this array, I should see that third element in the first spot of the array. So let me log the regular grid unsorted and the grid copy sorted. And let me just add to the end of draw no loop because I only want to do this once right now. Oh, beautiful. The first array is 5525, and then the second one is 2555. Wonderful. Now, what if there were 2 cells that only had 2 options left? The wave function collapse algorithm would say, take all of the cells with the same amount of entropy and pick randomly amongst them. Let's go through the array. I'm trying to think how to do this. I'm going to create a variable called stop and go through the array until I find one that has more options than the one previously. Okay, let's say length equal grid copy. I'm going to have a baseline length, which is the length of that first element of the array. I'm going to go through the array. If any given element has a length of options, and I'm always forgetting this, greater than what that first element does, break out of the array and save that stop index, because then I can say grid copy splice, starting at the stop index, all the way to the end. So how many elements? Splice removes elements from the array, and I want to remove from that element all the way to the end. There's got to be a more elegant way of doing this, but I'll just say grid copy dot length minus stop index. There we go. I have now sorted the array according to the entropy of each cell, and I have a new array with just the elements that have the least entropy. So now I can pick one randomly. So I'm going to pick one randomly from the copy of that array, and then I need to collapse that one. Let's call this cell. And then this is the pick is. Now, as is always true on the coding train, this could all be refactored in many more elegant ways, and I look forward to hearing all about it in the comments about how you're doing it. But basically, I want to pick the cell, collapse it, pick from its available options, and then I'm just overwriting the array. What should be left over is an array with one thing left in it. So if I were to do that, I should see either element 2 or element 0 with either blank or up in it. That's element 0 with up. Element 2 with up. So running this a bunch of times, it works. It works. We're getting somewhere. Breaking news. The live chat on Twitch is telling me that in the splice function, if I don't give it a second argument, it'll just remove everything until the end. Boy, I spent a lot of time working that out, and this is much simpler. We're not that far away, I think, from the end here. Let me get rid of these hard-coded options. Oh, sketch line 51. Oh, because the stop index. Oh, my stop index has a flaw in it. I will just say if stop index is greater than 0, splice it out. I removed everything from the array because they were all equivalent. Okay, there we go. So now this is its random first pick happening here. The next step is to reevaluate all the tiles and reduce their entropy where necessary. So for example, this tile right here, same entropy, but the one up top and the one to the right, the entropy changes because by picking that tile in the top right, it reduces the number of options that go to the left and underneath. I need to create a new array, which is the sort of next generation of tiles. If it's already been collapsed, then it's just a copy of what it was before, right? It can't change. It is what it is. And I can just bring it over directly. Otherwise, I need to look above, look to the right. I need to determine what are the valid options based on its neighbor up, to the right, down, and to the left. Here is where I need yet another data structure. I have 5 tiles. What if I had an array where every element of the array stored a list of valid neighbors? So what are the valid neighbors for a blank tile? Oh, wait. Oh my goodness. Each element of the array needs to also be an array. I could really think of this as a lookup table. Because I'm using numbers to number the tiles, doesn't really matter whether it's an object or an array, but you can kind of think of this as a lookup table because the 0 blank tile, it needs to have things that can connect to it up, to the right, down, or to the left. So I'm always going to store the information in this example in a clockwise direction. So the tiles that can go next to it pointing up are, like a tile that can go above this blank one would be another blank one, and then tile 1, because this does no connection down. So 0 and 1. To the right could be a blank one, and tile 2. To down could be a blank one and tile 3. To the left, we could put tile 4 could go there, or a blank one, 0 and 4. So now if I were to look at tile 1, however, and again, this is just me coming up with a way of doing this right now. There's probably a more standard or optimal way of doing this. I'll hopefully address that at some point later in this 700-hour video. But here, what could go above it? For tile number 1, tiles that could go above it are 2, 3, and 4, but not a blank tile. Tiles that could go to the right are, another 1, 3, or 4. That could connect below. Below is blank, so it could only be a 0 or a 3. And then to the left, what tile can go here? 2 can, 3 can, or another 1. The good news here is I've assigned variable names to each of these tiles so that it'll be easier for me now that I start to write this out in code. I don't have to remember the indices. I could just think if it's a blank one, the things that could go above it are an up or another blank. To the right, a right, or another blank. Let's start putting that in the code. So let me create a variable. I don't have to call it rules. Let's call it rules. Let's make it an object. Now, what can go next to a blank tile? Above it, we said could go a tile pointing up or another blank. To the right, a tile pointing to the right or another blank. A tile pointing up, above it, a tile that goes to the right, the left, or down is fine. Let me see if I can just quickly put in the rest of these. All right, I fit all of the rules here. I believe this is correct. I'm going to think about this for a bit and check the chat to see if I messed something up. All right, here's one that I found is wrong. For the tile pointing up, below it is either blank or down, and then to the left is right, up, or down. Let me address something. I think I've made this a little bit more complicated than it needs to be for this particular scenario. Maybe the way I'm doing my data structure is good for all broad set of possible tile arrangements. But in this case, even though I do have 5 tiles, each with 4 neighbors, each side is only one of 2 possibilities. So really, I could say this blank tile can only connect to other tiles that have a blank represented by a 0 on any side of it. This tile that is pointing up, I could say connect to any tile that has a connector, a 1, or that is blank, a 0. So really, for each of these, I only need to store 4 numbers, and then 0s need to connect with 0s, and 1s need to connect with 1s. I'm not going to double back and redo mine this way. Yes, I will. I'm just going to categorize the edges as A or B, or 0 or 1. But this is a good exercise for the viewer, looking at it in this simpler way about the kinds of connections that exist. So now we need to build what are the remaining options left. I need to build up what things I could be by looking at my neighbor. And only if j is greater than 0. So I'm going to look at the tile above me only if I'm not in the first row. Now, of course, I think if you look at the wave function collapse in the original implementation, it does wrap around, and that could be done here. But let's simplify things by just not looking at the neighbors above. Do I start with all the possibilities and then remove them if they don't exist? Yeah, that would be a way of doing it. So I'm starting with a baseline of this tile could be anything. And this should actually be outside of here, because I'm going to do this for all of them. Now I'm looking at the neighbor above and looking at what possible tiles it could be. Then valid tiles I could be are from the rules. This is the list of valid tiles. I'm this tile, and I'm looking at the tile above me. And maybe the tile above me only can be like left or right. So I need the valid tiles that go below down to a left tile. And I need the valid tiles that go below or down to the right tile. In the original array, up, right, down, left, the order is 0, 1, 2, 3. So I'm looking for 2. The rules for that particular tile, the ones that are valid down. I think I need to rethink my naming, but now what I want to do is look at what I have in my range of possible options. I'm going to remove them if they're not valid. You know what I should do? I'm going to make a function. We're going to have to do this so many times. Check valid, options valid. So I'm going to pass in, these are the existing options, and I'm going to pass them into a function to check if any of those options are included as valid. So somewhere else in my code, right here, this is the array, and these are the valid options. Is that the order I put them in? The array is options and what's valid. If valid includes array index I, great. So I want to check, or I'll say not. If the option that is in that array is not something valid, then I should remove it. It's confusing what are in these things, but let's just remember. Maybe a valid is blank and right. Basically what I'm doing is I'm going through every element of this array, blank, up, right, down, left. Let me see, is it in the valid options? Oh, if it is, that's good, don't do anything. If when I get to up, it's not valid, let me remove it out of there. This would result, so hopefully that helps you make sense of it. I don't love, maybe I should, I'll just say like current equals array index I. Maybe just element. So this maybe helps you read it a little bit. Let's look at every element in the array. If it's included, if it's not invalid, get rid of it. So now I think I could just do the same thing for all of these. Looking to the right, make sure that I is less than dimension minus 1. If I'm looking to the right, I want to know what's valid to the left of that one, which would be up, right, down, left. 0, 1, 2, 3. Let's grab this one for looking down. I probably should have checked this with just one of the rules first, but I'm just going to put it all out and we'll find out if I've gotten this totally wrong or not. I think this is good. If it's collapsed, I don't need to do any analysis. It's done. It's picked. If it's not, start with all possibilities, look up to the right, look down to the left, check that options array, and then at the end, next tiles index options, okay, are these new options. It's still not collapsed. I don't know if I need that or if that's redundant, but this is me updating that. And then after all of this is done, tiles becomes the next tiles. And so this can't be a const. Oh my goodness. Boy, did I just write a lot of code without testing anything. Let's run this. Okay, write.options is not iterable. Iterable. Oh, grid, not tiles, grid. Oh my God, I was using the images. I have an array called tiles, which is just the images. The array that I'm working with is called grid. Oh, grid. Let's call this next grid. So this can be a const, and this has to not be a const. All right, that's fine. Still have an error, but something slightly better, 147. So I just want to look at the rules for a second here. There's a flaw. The rules is an object. So if I were to say rules blank, why is that undefined? Oh, rules dot blank works. I guess I should just make that an array. I'm not sure what the best practice is here, but if I were to do this, this should fix the issue. I'm just going to make this an array. Since I have everything ordered numerically, I don't love this, but I think it should be okay. Oh, but now I don't need this. I don't need these. It's just gonna, I just have to have it in the right order. Well, I liked it better when I was referencing it with a name. I can't do everything right in this first attempt. Okay, we got down to 163. We got through all of these. Next grid index. Oh, next grid doesn't exist. So I just need to make it a new object. So I actually need to create the object. It's going to not be collapsed. It can be collapsed if there's only one left, but that'll happen by virtue of the next round. And then give it the options. Okay. No errors. Amazing. I'm just going to take out these console logs, famous last words. And let me now add, if I click the mouse, let me redraw, run through draw again. So it picked that tile. Okay, sketch.js. Okay, so I got an error the next time through. This is grid index. I forgot it up there. So if it's collapsed, don't get the image, get the other thing. Oh. I think there's a flaw in my algorithm. Let's just look at the grid. Oh, you know what I could do? I could do console table. So console table is a nice thing to just show me the array. This is the array. None of them are collapsed, and they all are 5 possibilities. Now, when I click it, I should see the first one is collapsed, and then none of the other ones. But what happened in grid copy? Oh, but they still all have 5 possibilities, which is absolutely wrong. So there's a big flaw in my algorithm for reducing the possibilities. Oh, by the way, when I copy the array, I need to filter out any elements that are collapsed. Filter is a higher order array function that will keep the elements where the function evaluates to true. So that should, and then so this can't be a const. I guess I'm gonna make another copy. Let's look at the grid copy also. So now I have all 4 with 5 options. And now I only have 3. I got rid of the collapsed one, which is good, but they all seem to have 5 options still. Let me look at my check valid function. I wonder if this includes is not right. This is a list of what's in the array. These are the valid ones. And so this should be left without a 0 and a 2. Oh! Why did I put those brackets there? It's a function that I'm checking if it includes that element. These are parentheses, not brackets. I don't think it worked still. Oh, this needs to be a 1. Splice. I did 0. 0 would take nothing out of the array. Wait, why do I have nothing in the array now? Oh my goodness. Ah! I need to accumulate all the valid things all together. I can't do them individually. Oh, this is totally wrong. This is a blank array. And then valid options should be itself concatenated with, these are the things that are valid, put them in the valid options. These are the things that are valid, put them in the valid options. These are the things that are valid, put them in the valid options. These are the things that are valid, put them in the valid options, and then check valid, options, valid options. So I've accumulated all of the valid options, and then as long as my option is valid across them all, then it should be fine. Is this right? I was so confident a second ago. No, it's giving me all the possibilities. Wait. I was so close for a second there. Oh, no, I still want to check valid. Individually in each one, I want to concatenate all the, I was right. I did it across everything, but I need to concatenate for each individual possibility. Hold on. I'm going to double back and explain this. There you go. That's the correct answer. There you go. Wave function collapse. Okay, hold on. It appeared in my head, and I don't know if it appeared in your head also while watching this. So let me see if I can go back and explain that. This is me. I am the tile. That's what it's become. Let's say the tile above me can only possibly be left or right. For whatever reason, it only has 2 possibilities. So what I need to do is look at all of the valid things that can be below a left tile and a right tile, concatenate those together, and then as long as anything I can be is included, it's fine. I think we've all suffered enough that I can change the dimensions to I don't know, let's just try 8. Well, look at that. Would you look at that? That is just absolutely lovely. I'm clicking. There's no need for me to click. I can get rid of no loop. And let's really go for it, people. Let's make the canvas 800 by 800 and the dimensions, I don't know, 80 by 80, 20 by 20. I've never been so happy to see a result. It broke. So I have a feeling that I'm going to need to add some backtracking to this. When in doubt, take out random seed and run it again. So close to making it to the end. Okay, so it can get to the end. Oh my God, I have more to add to this? I thought I was done. If grid copy dot length equals 0, return. Oh, no. Oh, let me put the drawing separately. Let me draw everything. And then if there's nothing left, if everything's been collapsed, return. There we go. Let's run it again. Isn't this delightful? 4 days later. I'm back a few days later, and I know you've been watching what is already like a very long video about wave function collapse, and I did get to a point where I made something, which is pretty great. I'm looking at this example of this printed circuit board, seeing that there are 14 tiles there. Some of those tiles represent 4 possible rotations. Looking at the way that I've implemented this code with an element of an array for every tile with all of the possible adjacencies, I think it would be incredibly difficult for me to hard code all of the possible tiles and adjacencies for a more sophisticated pattern like this. So I'd like to keep going, and instead of thinking of the tiles that I started with as 5 possibilities, I'm going to start with just 2 possibilities. And rather than enumerate what's possible here, I'm just going to categorize the edges as A or B, or 0 or 1. What this means is when I'm going to place another tile next to another one, a 0 has to match with a 0, a 1 has to match with a 1, and I could automate the rotation of this tile into its other possibilities, and then enumerate all of the adjacency rules with code. And I think if I create a tile class that keeps track of what image is it, and what are its edges, still going in the same order, top, right, bottom, left, that this will make the code more readable and easier to figure out and work and make for more fun wave function collapsing of everything. I think my brain is collapsing. So let me start by making the tile class. I had used the tiles array to load the images, so now I'm going to actually have an array called tile images. Now that I've done that, I only need to load the blank and up tile. The first tile can be the blank one with those edges. The second one would be the up tile with those edges. Now, what if I allow myself to create new tiles based on previous ones? What if there were a function that returned a new tile, which is 1 rotation, 2 rotations, or 3 rotations of another tile? So the rotate function needs to do 2 things: rotate the image and rotate the edges. So I make a blank canvas with the same width and height of the image, set the image mode to center, rotate by half of pi, or 90 degrees, times the number of rotations. So 1 would just be 1 rotation. Let me store the width and height in separate variables, which I think will make our lives a little bit better today. I'm going to call this variable new image because I'm getting confused between this dot image, which is that tile's image, and a new image. I have the new image. Technically, it's not a P5 image. It's just a P5 graphics object, but those two things are going to function the same way, so I think it's fine. Now I need to rotate the edges. So each new edge is the previous edge plus the number of rotations. Or minus, is it minus? This edge was previously down here, and the index values go 0, 1, 2, 3. So the new edge is the previous edge minus 1. However, if I'm edge 0, minus 1 isn't negative 1, it's 3. It's got to wrap around and get index 3. A way I can do that is, let's create a variable to store the number of edges. I can add that to the total. So 0 minus 1 is negative 1 plus the total number of edges of 4 would be index 3. But if I'm 2, 2 minus 1 is 1 plus the total number of edges is 4. So I'd get 5. So all I then need to do is use the modulo operator. And this should give me perfect wraparound. Always take the previous one, but if the previous one is negative, you're going to get the higher value. And it's not 1, it's the number of rotations. So now I can return a new tile with the new image and the new edges. So before I go any further, I just want to determine if this at least worked rotating these images. The difference now is the image is a property of that tile object. Something is wrong. My rotation is not working. So I've made a sort of classic error in P5 here where I didn't think about the origin around which I was rotating. So I've rotated the image off the canvas that I'm drawing it to. I need to say new image, translate to the center, then do the rotation, then draw the image at 0, 0. So if you zoom in, you'll see that the tiling is a little bit askew. That's really just because when I made the images, I didn't make them perfectly symmetrical, so the rotation isn't perfect. But I kind of actually like the way that it looks with it slightly askew, but this is not relevant to the algorithm. It's just a matter of designing the tile images, and ultimately, I'm going to use the tile images from here to see if I can create a more sophisticated pattern. So now, instead of having this big array that's just a mess of all of these rules, could I procedurally generate the rules by analyzing the tile objects that I'm creating? And as long as I'm doing that, why not put in the tile object itself lists of valid neighbors? This is terrifying, but I'm just going to delete all of this from the code. Now that I have tile objects, looking down here, it would make sense for me to have a cell object. I mean, I have cell objects. They've got a list of options as well as whether they're collapsed or not. But I should make a class with a constructor to generate these. These names are no longer relevant. The list of options can just be the index values to the tiles array. So what I want to pass in is the total amount of tiles there actually are. Then I can fill the array with, if there are 5 options, 0, 1, 2, 3, 4. Of course, that could be done with some higher order functions like fill and map and from, and have a ball doing that. I actually just spent a little while doing it myself, and it was very confusing, and I didn't want to include it in this video, but here's what it looks like. Loaded and created the tiles. I built a cell for every spot on the grid. And now I need to generate the adjacency rules based on the edges. For every tile, I'm going to just write a function called analyze and give it all the tiles, all the other tiles. So the tile object's going to have to figure this out. Let's call this the connection is edges index 0. Now, if we look at all the tiles, I mean, we should check if a tile can connect to itself. That is a valid thing to check. So I'm looking at all the tiles regardless. So if my connection up is a certain value, I need to find all of the tiles that have that same connection pointing down, which is index 2. And I'm sure there's a way that I could not do these as 4 different loops, but I'm going to do it that way right now. And maybe this secondary variable is kind of unnecessary. And this is tiles index I. And this might actually be easier to read. The order of the tiles doesn't actually matter. So let tile of tiles. So if that particular tile's down edge matches the tile that I am, my edge, which is this dot edges, then it's a valid connection. So now I just need to repeat this for right, down, and left. Oh, and I don't need to do a separate loop. They can all be in here. So right is 3 is equal to 1. Down is 0 is equal to 2. And left is checking if this tile's edge at 3 is connected to the tile that it's looking at, its edge at 1. Now, again, there's probably a lot of redundancy here, but this is just the way that I'm getting started here, trying to recreate what I did originally in a bit more of a generic, scalable fashion. I think this order makes more sense. We're loading the images, rotating the ones we need to rotate, and defining what all the edges are. Then we're analyzing all the tiles against each other to see which tiles can go next to each other. Then we make a grid full of empty cells. Each cell could be any given tile to start. So drawing doesn't change. This, however, is the part that needs to change. Before I was looking at my rules array. Now I need to look at the adjacencies that are defined in the tile objects themselves. So up, looking at the cell up. Valid options starts as a blank array. Then I need to look at what are the possible options in up, and then get the valid ones now are not rules, but tiles dot down. Anything that I could place where I am has to be something that can be below all of the things that could be next to the tile above me. Is that the only thing I'm changing? Look at the tiles and look to the left, then look to the tiles, up. There's no way it's as simple as that. Okay, cell is not defined. Okay, well, that's an error I can fix. Include the cell file. Blank is not defined. Where did I have blank? Let me, by the way, change the dimensions to just 4 by 4 while we're sort of figuring this out. Ah, so the options are, when I'm assuming it could be anything, let's use the fancy higher order array functionality thing here. I need an array with the number of spots in it as the number of tiles there are. I need to fill it with something to start, so I'll just do 0. And then I can use the map function to map every value to its index. So that's its current value, which is 0. Its index is I. If I've done my higher order array functions correctly, it's an array that has, with 5 tiles, has the values 0, 1, 2, 3, and 4 in them. Okay? Cannot read properties of undefined reading up. Well, this is a good start. 137. Tiles, option, up. What is going on here? Hi, everybody. I've been debugging this for a little bit. And part of my debugging, I said console log the grid. And I'm looking at the grid, and the first time I get 4 cells, because I made it 2 by 2, only one option left, because that one's collapsed, 5, 5, 5. And then suddenly, look at this. Cell, then brackety, brookety, brackety, brackety. Those aren't cell objects, because I did something really pretty terrible. At the end, instead of creating the new cell object for the next generation, I'm just making an object literal, which is not right. So I need to say new cell, and the options shouldn't, this is when a new cell is made. How about, I could give it options. I'm trying to think of an elegant way to design the constructor now. So I just did a little testing in the console here that I can determine if a variable is an array by saying instance of array, and I'll get true. So I think what I can do here in this cell class is I can say if num is an instance of an array, then this dot options equals that array. It's no longer num, it's the array. I mean, I don't know what to call that variable. I'll still call it a num. Otherwise, I'm filling an array with all of the options according to some total. So let's just call this value to be a little bit more generic. So these are the 2 different ways I can create a cell object. And if I go back to sketch.js, I should be able to say, make a new cell out of those options. Oh, that's better. I see 4 cells and 4 cells. I still got this error though. Something is going very haywire here. I'm going to have to do some more debugging. Oh, please hold. If tile 0 is collapsed, I should see 1 option there. Tile 1 should have 3 possibilities. Tile 2 should have 2 and not be collapsed. And tile 3 should have all 5 possibilities still. So cell number 1, which is the one directly to the right of the top left, should have 3 options left, and it has 0. So the bug is there, and cell number 1 is when I is 1 and j is 0. So I have an index. So I can debug some things if index is 1. Let's check looking to the left. So if index equals 1, let me look at the tile to the left. The tile to the left is collapsed, and it is tile index 1. So its valid options should be all of the things that can go to the right of tile index 1. Aha! The error is not a logic one. It is an apples checking against oranges problem. The valid tiles are tile objects. But my function that I wrote days ago at this point now in the check valid is checking index values against each other. So if I go back to this analyze function, I shouldn't be putting the actual tile objects in the arrays that are valid up, right, down, and left. I should be putting the index of that tile. So I do need to have this a for loop with I in it, because the index of the tile is what is indicating what's valid. Ta-da! We did it, people! Okay, let's get rid of some of the debugging. Let me go back and make it 20 by 20. Wave function collapse, exactly what I had before, but now, and again, it's not always going to find a solution, and I got to talk about how to deal with that. But now, I don't have to create a massive map of all of the tiles and their adjacencies. All I need to do is load tile images and some numeric indicator for what's a valid connection of an edge. Then I can rotate tiles and infer all of the adjacencies. This means I believe I can get this PCB generator going. Thank you to those who are watching live who sent me fixed tiles and the circuit board tiles. I'm going to download those now and see if I can bring them into my sketch. So I have the circuit tiles and I have my code. I think I'm going to need to kind of draw my own version of these tiles on the whiteboard to enumerate all of the edges. So there's a blank gray and a blank green tile. Let's start with those. That's tile 0. This is 0.png. These numbers, by the way, aren't really relevant, although they will be because they'll be the indices into the tiles array, I guess. And 1.png. So the blank one will have zeros as its connectors, edges, and the blank green, I'm just going to say this is blank, and this one is green. It'll have ones. Okay, what is 2.png? Kind of looks like this. All this area is green. So that's a 1, a 1, a 1, and now we need another thing. This is a 2. And this is like gray. So green is 1, and this is something new. It doesn't match this because this is green. 3, 3, 1. So I've worked all this out, and there's only actually a few different kinds of sides. There's a blank side 0, a full green side 1, a light green connector, which is 2, a light gray connector, which is 3. That's what all of these are, except for 4.png and 5.png. These are not symmetrical, meaning if I flip them, I have a different tile, which is different than how I'm rotating things. So I think I need a whole other mechanism for tracking how these connect. So for right now, in this process of working this through, I'm going to do this without using these tiles. So I have 13 tiles. Ordinarily, I would just write a loop now to load them into the array based on the number of the file. But since I want to skip 2, I'm going to do it manually. Okay, so you can see I'm loading them into an array of 11 tile images, skipping 4 and 5. Now I put in the connections. Zeros, all 1s, 1, 2, 1, 1, 1, 3, 1, 3. I really want to try this without rotating any of them and see what happens. Images are in a directory called circuit. Oh, I've never seen anything so beautiful in my life. That's amazing. That's promising. So now I just need to do some rotations. Now looking at these images, they don't all need to be rotated 4 times, but I might as well because then I don't have to think about it. So let index equals 11. I'm going to skip, obviously, 0 and 1. I'm going to go through all of the tiles 1 through 10. Oh, I shouldn't be in preload. What am I doing? I'm going to go from 2 all the way to 10. And I'm going to say tiles.push, tiles index I, rotate 1, 1, 2, 3, so less than 4. So that should go, skipping the first 2 tiles, which don't need to be rotated. Now, there's a lot of extra rotations I don't think I need, but starting with tile 2, going all the way down to tile 10, rotating them once, twice, and thrice. Oh, I don't need this index, because I can just push them into the array. Wow, this is wild. I guess the blank tile never shows up. Tile 0, it only can connect to tile 4. I'm so close. I think I could get image 4 and image 5 in there. No, I can't. One day later. Welcome to day 3. This time, I'm finally going to complete the wave function collapse algorithm. First, I need to say a huge thank you to Telemaco and Garazbalg, who overnight, while I was sleeping, added some GitHub issues on the wave function collapse repository, pointing to the keys to unlocking the asymmetrical tiles and placing them correctly that I was struggling with yesterday. An incredible demonstration of the solution I'm about to attempt is Oscar Stahlberg's Unity implementation of wave function collapse. In it, you can interactively start to select tiles, and it will visually show to you which tiles are left. You can also let it run and watch the process as it selects the tiles, and the magic of wave function collapse unfolds over the screen. The beautifully designed tiles of this demonstration are not symmetrical along the edges, but each edge can be divided into 3 parts: the left part, the right part, and the middle part. And as long as brown matches with brown, blue matches with blue, half brown, half light brown matches with half light brown, half dark brown, the process will work. And thanks to the magic of these colorful markers, I have redrawn all of these tiles, so I think I can make a key to enumerate all of the possible parts with each edge divided into 3 that could be on any tile, symmetrical or not. So this first tile, which is all black, is fully symmetrical along all the edges and all rotations. And I think because I've numbered all the tiles, it might be easier for me to use letters here so that we can really distinguish what's being matched with what. So I'm going to call the black color A. White, which really is a dark green in the actual tiles, I will call B. Now, this side will be A, 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 A. One color all around all the parts of the edges. Same for this, but with B. Finally now, with the image number 2, we will get something a little bit more interesting. We've got Bs all around these sides. Those are some very funny Bs. And then I've got a B here and a B here. But now I need a third color for light green. We'll call that C. The blue color here is actually gray in the image files, a new color. We'll give that the letter D. So now I have B, 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 D, B, and so on and so forth. Now we've got something pretty interesting, the asymmetrical tiles, but this system makes them really easy to notate. And I can go on and complete the rest. How did I do? I think I've got this right. One mistake. Thank you, live chat. So now back to the code. First thing, I can turn this into a loop, which is going to make all of our lives so much better. Don't you just feel so much more at ease and relaxed? Tile images. Ah! No, I'm not relaxed at all. In fact, I'm totally panicking. That would have been very unfortunate to find later. But now, Nonetheless, these tile objects still have to be created individually because I'm going to manually notate all of the letters for the edges. And by the way, there's a key term that I should be using when talking about all of these edges, and that is the term socket. You can think of each section of an edge as a socket. Each socket must connect to another socket of the same type for them to match up. And by the way, I encourage you to try having more than 3 sockets or fewer than 3 sockets. So many possible things you could do if we could get this working. The one thing that's going to be really confusing is what is the order by which I write the letters for the sockets? This side socket is BBB. Well, this side socket is also BBB, and I don't have to worry about what order because they're symmetrical. But this one I really have to think about. This side socket is ABB. Does it connect to itself? Well, you might think it does, right? Because what it wants to connect to is something that looks like this. A matches up with A, B matches up with B, B matches up with B. But if I took this side and put it here, I would have to do that by rotating this all the way around, and suddenly this side rotated around would look like this. These don't match. But this side, if I were to take this side and bring it up here, it would match. But this says ABB. These are not the same! While this one says ABB and this one says ABB, those aren't the same orientation. I need to make sure I'm notating everything in the same order, which means in the clockwise order. It's the way I've been thinking about this project all along. Up, right, down, left. Up, right, down, left. So even though I most definitely want to draw it this way, because it'd be way too confusing for me to write BBA and not see that match up, when I put it in the code, I need to notate the sockets as ABB, BCB, BBA, AAA. Then edges need to match up with other edges that are inverted so that they lock together. And I also should note that another way to approach this order would be north, east, south, west, which I could have been doing all along, but somehow my brain is going up, right, down, left. So now as I prepare to enter the edges into the code, looking right at the whiteboard, for tile 0, this is easy. It's just going to be AAA in all 4 spots. Tile 1, all Bs. Now with tile index 2, I've got the top as BBB, but I need to make sure I read BCB in this order and BBB in this order. Oh, but these sides are symmetrical. So again, it's only going to matter when I get to 4 and 5. And here I am at index 4. ABB, that's the top. BBB, that's the right. Now for this one here, even though I'm wired to read it from left to right, I need to make sure I enter it from right to left, the way that it would look if I had flipped it, rotated it, so that this side were on the top, BBA. And then the last edge is AAA, from bottom to top. You might be asking yourself, isn't there a way to automate this? I mean, do you really have to enter it in manually, 1 line of code at a time? And the truth of the matter is, there's probably a way we could look at the color values of the pixels along the edges and generate the sockets based on those color values. But that's a project for another time. I'm going to stick with doing it manually here. Let's do the rest of them. Sorry, one error here with tile index 4. That's BCB. So now that everything's in here, what else needs to change? Certainly the way I'm checking if 2 edges are compatible, if the sockets fit together, that needs to change. Let's just run the code and see what happens. There's bound to be an error somewhere. Amazingly, I'm not getting an error, but I'm also getting a pattern that isn't exactly what I'm looking for. Well, now I got an error because it came up against a tile where it couldn't figure out what goes there. And here now we're seeing a strange pattern that I don't even recognize, but I do kind of love. So what I'm doing currently in the code is checking if one side is equal to another side. So can BBB go with BBB? Yes, those sockets connect. But back to here, can ABB go with ABB? No, those don't connect. But ABB could go with BBA. Remember, this side is really BBA. So all I need to do is, instead of checking equality, I need to check if one edge is equal to the reverse of another edge. And I believe that happens in the check valid function. No, this isn't it. It's all about how I generate the adjacency rules. Check val is just checking to see based on the adjacency rules. So I need to regenerate the adjacency rules, which is in this analyze function. And here I'm checking if tile.edges, here's where I'm checking if one edge is equal to another edge. So let's write a function, compare edge, return A is equal to B. Is there a string function called reverse? There's an array function called reverse. So I think I need to write my own string function to reverse a string. That's not too hard. I could make it into an array. I think split takes a string and puts it into an array. Then I can reverse the array and then join it back together. I think that'll work. And then now I can just say, compare tile edges 2 with this dot edges 0. And that's called compare edge. Now I want to compare 3 and 1, 0 and 2, and 1 and 3. All right. Are we ready? Is this going to work? We're about to find out. List.reverse is not a function. Oh, I've got to give it an empty character from which to split. So just like I need to join them with an empty character to put it back into a string, I need to split it with that empty character. Oh no, there's a function in P5 called reverse. Oh, P5, I love you so, but you always have these global functions which confuse me. So the reverse function in P5 actually does the work of reversing the array, but it does say deprecated. It will be removed in a future version of P5 because there already is an array.reverse function. So that all makes sense and everything is right with the world again. I just need to call this reverse string, which is more clear anyway. All right, you've waited long enough. Let's see. No, shoot. Assignment to a constant variable. I made it constant. Let. Oh, look at that. Oh, it's so beautiful. No, but that's fine. That's just the thing where it gets stuck. I'm going to put my random seed back in just to sort of track the error. Well, that one didn't have an error, but it is lovely. I can't seem to find the random seed that will give me an error. Aha, there we go. We got an error. So the error happens on line 136. So tiles option is undefined. Let's see what's in up.options. This really slows it down to console log every thing that it's looking at, but we'll see. There's a weird clue here. The array isn't empty, like there's no options left. It's got one element, but that element is undefined. And there's only one place that I put manually one element into the array. It's this sort of weird way that over here, I pick from its options. And if there's no options left, what I pick will be undefined, and then place it in the array. So I think I have to say, if not any pick, what do I do? Start over. Well, let's just say no loop and return. See what that gets us. So I think there's some optimization and cleanup I could do in the code, and ultimately implementing backtracking, going back and trying a different solution would make sense here. But I'm just going to keep things simple and have it start over. I'm going to write a function called start over. In setup, I create all the tile objects. I put them into a big tiles array. I analyze all the adjacency rules and then create a new grid. I think I could just start over by creating a new grid. So we'll call start over also in setup, then create the new grid and start over. So if we ever get down to a cell with no options, we'll start over. There we go. So let's see how many times I have to run this before it fills. I got one. But the chat is rightfully pointing out something that I didn't consider, which is that if not pick is causing a lot of false positives, because one of the options it could legitimately pick is 0. So I have to just actually say, if pick is not equal to undefined, just make sure it's not undefined, then you can keep going. Or if it is undefined, sorry. If it is undefined, you can keep going. No, if it is undefined, start over. If it's not undefined, keep going. I think we finally have it, people. Let's run it one more time. Yeah, now it's getting further along before it will reach that error. There, now it got the error, and now it's going. There we go. I think this is our second attempt. Yay, and we did it on the second attempt. Amazing. Now, let's do something really exciting. Let's get rid of random seed so that it'll do it differently each time we run. The canvas is 800 by 800. Let's try upping the resolution to 40 by 40. My guess is it's going to run very slow because I haven't bothered to think about are there ways to optimize the performance, but let's see what happens. Wave function collapse! We have it, everybody! There is so much more to do here. First of all, I haven't even attempted the overlapping model. I'm gonna wait until you're sometime in the future actually watching this. This is a video on YouTube, so I can get a lot of comments and feedback, because I'm sure there's lots of things that I've done in sort of strange and odd ways that I might want to think about and address before I move on to the next version of the algorithm, which detects the tiles and adjacencies in a way based on doing a pixel analysis. That's a little hand wavy, but that's the general idea. I also have left out a key element of the algorithm, which is explained really nicely in this processing forum post from Solib. The process doesn't stop to the 4 direct neighbors of the collapsed cell and has to be extended recursively to the neighbors of the neighbors and so on until all constraints are propagated. I'm kind of getting it to work anyway because I'm just doing a full pass through everything every time through draw, but ultimately I could reduce the entropy by recursively propagating the cells as their options start to collapse. Now, in truth, this tile set that I'm using doesn't really need this because a tile, when it's collapsed, only affects its immediate neighbors, and that doesn't really ripple out in the same way that it might in, say, Sudoku. But this is definitely something that I would want to add to the algorithm in a future version of this. So give me your tips and thoughts about how to do that in the comments. Of course, there's backtracking, would love to add that. And then, but really, this is what I'm here for. This is why I made this video. What possible tiles could you design, and what patterns and beauty could you create by just using my code exactly as is, not changing anything, but just designing your own tiles, creating your own key of sockets, and just running it and letting the beauty follow. I want to see this so badly. Not to mention, this algorithm can be applied in 3D, and whoa, there are so many amazing implementations of wave function collapse in 3D. YouTube videos, websites, I'll try to link a whole bunch of them, put them up on the screen. There's just too many to mention. So comment on the video, go to the Coding Train website where there is a place that you can submit your version of this. Tag me on social media. I want to see the world full of beautiful wave function collapse algorithmically generated images. And stay tuned for the next coding challenge or sometime in the future when I tackle the overlapping model.